Welcome to Screencast 2. We're continuing with information we need to complete Lab 1. Again, Lab 1 will be mainly concentrated in two parts, and that will be a circuit in which you'll verify Kirchhoff's laws. You've done this before in the 200 level class. This will be many more, 6 resistors, so not like a few of them, but 6, but it's going to be these kind of mechanical voltage loop rule and junction rule. However, it will be very good getting you set up with the breadboard, your introduction to the breadboard and designing circuits. Conceptually more important though, so this will be good for your technique and your experimental technique. The Thevenin and Norton equivalent circuits and voltage divider, this is part of the lab too, and these are going to be more helpful throughout the course for your conceptual understanding. So the lesson plan for this screencast will be a sample Kirchhoff circuit. You can already see it below here. Light bulb questions. These were like the ones that you just took the other day on the concept inventory. These really probe whether you know what's going on in these DC circuits. So for concepts, these light bulb questions are way better than the Kirchhoff ones. And then we'll go on to the Thevenin, Norton, and voltage divider. With the voltage divider comes the concept of input and output impedance, which will be carried throughout the course. So the voltage divider and input and output impedance, these are big things that we're going to take with us. Okay, let's go back to something you've seen before, and this is a more simple circuit of what you've seen before. We have a battery. It doesn't have to be one, could be more than one, and we have resistor 1, that's supposed to be resistor 2, handwriting's a little bad there, and then resistor 3. And so what we'd like to do is we'd like to figure out the currents going through. Get used to this language, currents go through a resistor, not across. Voltages are dropped across a resistor. Alright, so we want to find the voltage drop across R1, R2, and R3, and we want to find the currents through R1, R2, and R3. So the first step you do if you want to do this is to just assign some currents, and as you know from before, if you're wrong on the direction of the current, you'll find out in the end. The sign will take care of it for you when you do the math. Alright, so here's what I'm going to do. I'm going to call this one, I'm going to call that one I1. Oh, let's try that again. Okay, you have to bear with my handwriting as I'm getting used to the iPad here again for drawing. I2. And then we are going to call this one I3. I'm going to make it kind of go around the corner here. Okay. And then, of course, I should actually, let me actually try to draw some junctions here. Fill that in a little better. We know that I1 is going to be coming out of here. Okay. Hopefully you can see that down here. Let me erase that and make that a little better. Alright, simple like you've done before. Now what we need to do is we're actually use the loop rule and the junction rule to try to put this into a set of algebraic equations that we can solve for I1, I2, I3, and V, etc. So what we'd like to do is we'd like to make a set of equations, and what you need to know for this problem is, here's what we'll assume as it will be in your lab, is that you know R1, you know R2 and R3, and you know the voltage V. But what we don't know, this is what we're going to assume, is we don't know I1, I2, and I3. Alright, so what we need to do is we need to use the Kirchhoff junction rule and loop rule to build up 3 independent equations, and then we have 3 unknowns and we can solve for each one. Let's start with the junction rule, and we'll start at this junction here. The junction rule, again, is the sum of the currents going into the junction is 0, or you can also say that as the sum of the currents going into the junction must be the same as the sum of the currents going out of the junction. So let's look at this one right here. You can see this one is simple. I1, we can write I1 is equal to I2 plus I3. So let's write that up here. Okay, and so we have I1 is going to be equal to I2 plus I3. Okay, there's one of our equations. Let's move on to, we could do the same thing. As you can see, we get a very similar equation down here. So that's it for independent equations, at least of the circuit for the junction rule. Let's go to voltage loop rules. And let's start with this loop right here. So we're going to start, I like to start at the battery if we can, and I can think of it, it's going to start dropping voltage as I'm going with the current back to 0. So what we have is we're going to have V minus I1 R1 minus I2 R2 equals 0. Okay, let's go to this one over here. This is kind of a funky one. And we can choose, I'm going to choose to go around this direction. We could go around another direction instead, but so I'm going to go I3 R3. I'm going with current, so I3 R3 minus, because now I'm going to go against current, I2 R2 is going to be equal to 0. Okay, and then let's finally do the outer one. That one will be V minus I1 R1 minus I3 R3 equals 0. And now we have 4 equations, and we have too many, so we need to look for independent ones. So let's circle this one. You can see that if you multiply this one times minus 1 and add it to the equation up here, the second one, you're going to get equation 3. So let's just take the top 3. Those should be independent equations. Here are those equations written a little bit sloppily, but at least organized. So you can see that I'm organizing them by current. All right, these are like columns of current, I1, I2, I3, and you'll see why in just a second. Okay, so now we're going to actually, because this is a set of 3 algebraic equations, linear equations, we can use a matrix to solve them. So let's build that matrix. And so here's what's going to go in the top row. 1, minus 1, 1, R1, R2, 0, and then we'll get minus R2, oops, forgot my 0 there, and then R3. All right, that's not the equation though, you'll see I'm trying to represent it. So then these will be I1, I2, and I3, and that's going to be equal to 0, V, 0. All right, so now what we have is we have a matrix equation, is that A, this will be called matrix A here, okay, that's A, is going to be equal to, times I is going to be equal to V. So A times I will be equal to V. Okay, so here's the A matrix, this is the I matrix, and this is the V matrix. All right, and what do we want? We want to solve for I. So what we need to do is we need to multiply by the inverse of matrix A. So if we want I by itself, I is going to be equal, we're going to have to basically multiply from the left by A inverse. So if I multiply by A inverse here, that gets rid of the A and leaves I, but I need to multiply the other side by A inverse as well. And that's it. So this doesn't involve a lot of intuition, it involves a lot of careful bookkeeping and algebra, and setting up the circuit to make sure you measure the right components and have it wired right is actually going to be a little bit tricky. So this is why we're going to take an easy, well, a circuit that doesn't have much concept with it by looking in this light to help you build it and then help you verify it. So many of you might have tools to do matrix manipulation on your calculators. Most nice graphing calculators can actually do pretty complex matrix math. If you don't, I suggest to go to Wolfram Alpha. It's a pretty handy online tool if you haven't used it already in your classes. And so all I did is typed in Wolfram Alpha in Google. And then I just typed in matrix inverse because that's one of the things we wanted to do. And it shows all the different ways of inputting a matrix into Wolfram Alpha and doing computation. So let's copy a bit of this line here just to show you what it does. Oh, this will let me use the browser. There we go. I don't think it'll let me copy and paste easily, so you have to bear with me as I type it in. So I'm going to type in curly brace, 0 minus 1. Oops. And what I'm doing right here is this will actually be, this is going to be the first row of a matrix. And in fact, let's make that 3 big. I don't know, we'll just add in a 1. We're just going to make up some values. And then let's type in, this will be a new row of a matrix, so I don't know, 0 to 4. Oh, I forgot my commas. And I'm slipping on the typewriter here. 0 to comma 4. Curly brace ends that row. And then, oh, comma, let's do a last row. Just making things up here just so you can see how it works. Okay, this actually should... maybe we'll just stop right here. This actually just should create the matrix if I did it right. And so let's hit equals and see what it does. There we go. Okay, so you can see my matrix is 0, minus 1, 1, 0, 2, 4, 1, 3, 1. Okay, and so now we can actually do some math on this. Let's go back up here. And I don't know if you remember, inv was the way to take the inverse of it. And we'll see if I left out another bracket, it'll yell at me. Okay, so it did it. So that was fine. So it's taking the inverse of that. So that's how you do an inverse. We could multiply by another matrix. Now, if we want to multiply by a 1 by 3, right, we're going to have to... or a 3 by 1 rather, we're going to have to switch how we do the orders up here. And also, if to multiply, you're going to use the dot, all right, to take the inner product. And now what I'm going to do is, let's see, this will be the entire matrix here, and now I just want 3 single numbers, and that will give me a row. So let's give this a try. So I'm just going to put in 1, all right, and so each single number will serve as its own row now. Okay, and let's hit equals here and see what we have. Oh, come on, there we go. See if I did that right. Cool. Okay, so now this is what you'd want to do for the case that we just showed, where it's a 3 by 3, and each of these would represent. This would represent your inverse A matrix. This would represent the voltage, and so now these would be the individual values of current, I1, I2, I3. Of course, use your calculator, that's fine. One thing, don't get too frustrated when you're doing these 6 equations. You have to pick 6 independent ones, and I would just say try to see if you can find redundancies. Other than that, guess. If it doesn't work, pick a different set of 6. Okay, when you're doing your lab notebook, I want you to do the theory here to predict it. You're also going to be using multisim, and I'll give you some example programs on that. Multisim will help you simulate the circuit before you do it. So then you can actually build this circuit that you're going to build in lab before you build it in lab, and run it and actually see what voltage and currents the simulator predicts. And this is a circuit building software, not something like Mathematica. Okay, your circuit's going to look something like this, where you have 6 resistors, and there's just something I wanted to point out when you simulate it on multisim software. First one thing is you'll put in the values that are in the lab, and invariably you'll find you cannot find the resistors you want to find in the lab, and so you'll substitute other values. That'll be the same for capacitors, inductors, for some of the other components. And so what we want to do is we want to still simulate and calculate what we think we're going to have, but be prepared to be a little disappointed because you won't necessarily find all those components, and even if you do, their tolerance might be way off, that it's not going to match exactly. However, it's going to match close, and what we're interested in is the behavior, not the exact precise numbers. If we really are interested in the exact precise numbers, we'll measure our components and we'll go back and simulate it again and go back and forth. But something I just want you to take note of is you're going to have two voltage supplies, two power supplies. In multi-sim software, they want you to put a ground on the circuit. And so where do you put a ground? You could put a ground on this one and this one, or you could put a ground just on this one, or just on this one. And those are actually two very different cases. All right. What would happen if you put a ground on this one and this one? Pause it maybe for a little bit. All right, maybe you paused it. I paused it a little bit too. If I put a ground here, then this is effectively 0, and this is effectively 0. I might as well throw away resistor 6. It's not in there. Okay, so in some ways it doesn't make sense to ground both of these batteries. This is a case where one is at least meant to float. So in lab, if you tie one of these to wall ground, the third prong, which is the earth ground, and you tie the second one, then you shouldn't get anything through resistor 6. If you tie one of them to the ground and leave the other one floating, then the one that's floating is going to float to whatever it wants to, depending on the other values of the circuit, and it won't necessarily be 0. Okay, so the way the circuit is set up, it's meant to be that at least this one is floating. You could float both of them. However, in your simulation, it's going to yell at you if you don't have at least one ground. All right, so in your simulation, you can ground either one of them. All right, and in lab, you can leave both of them floating, or do the same thing where you actually ground one to the earth ground. Now let's do some light bulb problems. I like these so much. These really test real electronics intuition. The Kirchhoff problems, again, good practice, I think, for kind of warming up. But what we find is that students know how to do Kirchhoff problems, but they don't know which light bulb goes out, which one goes brighter. And these are the concepts that I'd like you to take away from the course. More than just light bulbs, but when you get to capacitors, inductors, and things like that, can we do these more complicated things, transistors, and have some kind of intuition about what's going on? That'll take you way farther the next time you see a circuit board or the next time you have an electronics class or project. So in these light bulb problems, we're assuming that the power supplies are perfect, that they will give exactly the volts that they say no matter how hard you load the circuit or press the circuit. This doesn't happen in real life. If you load a circuit, the poor pump man in the fluid flow analogy isn't going to be able to keep up, and it's going to load the circuit and the voltage is going to go down. So even though your battery gives 10 volts, if you put on too small of resistance, you short it out, that 10 volts is going to go down towards 0 because you're just going to draw too much current from it. We're not assuming that here. We're assuming that they're perfectly stiff voltage supplies, and that if you were to draw infinite current, they would. That sounds really unrealistic, but if you design a good circuit, you're going to design it so that it's never actually pressed that far. So these are still decent problems. They're not fake problems, but we're just not going to press the voltage supply so hard. All right, the first one, this one's not so bad. So basically you had a light bulb that was on, and now you jumpered this wire over. What happens when you add the wire to the light bulb? What happens to the current? All right, I'm going to let you pause these on your own, and then we'll answer them together. So what happens is all of the current goes through the wire. If this light bulb, we're assuming the light bulb is a resistor. It's a nonlinear resistor, but let's just assume it's a straight resistor for these problems. Then it has a chance, the current has a chance to go through 0 resistance or some resistance. It's going to choose the path of 0 resistance, and all of the current is going to go through this jumped over wire here, and none is going to go through the light bulb. You basically shorted out the light bulb, so it's going to take a path around the resistor. All right, these ones are a little bit sneaky. 2 maybe is sneaky. What is the voltage at this point right here? All right, I have a 10-volt battery and I have a resistor, and so what should the voltage be right there? The answer is 10 volts. There's nowhere for this is a broken circuit. This is not connected, and so if this side of the battery is at 10 volts, here's a resistor. There's no current flowing through it. It's just a piece of semiconductive material, or material that isn't purely conductive. You're going to have 10 volts right there. at respect to ground. Again, our volts. So this is almost kind of silly, right? What happens if you put a voltmeter right here? You'll read 10 volts. All right, you have basically an open circuit. If I take this resistor away, what do I measure there? 10 volts. All right, there's no current flow through here. So there's 10 volts here and there's 10 volts here. That'll help answer this next one. What happens when I connect it with another resistor? Well, what's the voltage here? Again, pause it. Well, if I tell you the resistor values, you might be able to get it exactly, but here it's less than 10 volts. So now we have current flowing through the circuit and some voltage dropped, so it's something less than 10. This resistor might have dropped 3, and then this one would drop 7. This resistor might have dropped 5, and this one would drop 5. Whatever it is, it's no longer 10, because now we have current flowing through and it's dissipating power. Cool stuff. Let's keep going. And thanks for putting up with these kind of cruddy drawings. It's still a little bit better than the grocery store, electronic pen that you sign your name for your credit card. But you can tell that this isn't whiteboard nice. But hopefully it's legible enough. All right, let's look at number 4 right here. This one I think is kind of tricky. So what happens when you close the switch to the light bulbs? All right, let's think about what happens when the switch is open. And this one I think it helps to draw. Let's kind of rename some of these voltages here. So here's what I'm going to do. I'm going to call this one 0 down here, 0 volts. I like 12 here. Let's call this 12. Okay. But now check it out. This one is 12 volts here. And again, this check it out. This isn't ground. This doesn't mean it's 0. It just means that this point here is 12 volts lower than that point here. All right, this tests your knowledge of do you know what a battery is, how voltage and power work. So if this is 12 volts here, right, this is 12 volts. I called this 0. The battery gives me 12 above it. All right, this is on these are connected here. So this is 12 volts down here. Let's just write that so we realize that. This is also 12 volts then at this low side of the battery, and that means that this is 24 volts up here. Oops, 24 volts. Cool. All right, do you get that? It's getting a little crowded here. So if this is 0, that's 12, that's 12, that's 24. And so what we see here is 24 volts with the switch open here. It's 24 volts that gets dropped across these two bulbs. Okay, if they're equal resistance, we're going to have, and we're assuming they are, you're going to get 12 volts dropped across this bulb, and then 12 volts dropped across this bulb. All right, so what we'd have is we'd have 24 here, 12, and 0. Do you get that? So with the switch open, 24, it drops half of it to 12, drops the rest of it to 0. Let's see what happens when we close the switch. Well, when we close the switch, look, this is 12. And this is 12. Wait, wasn't that 12 before? So here's what happens, nothing. In this circuit, when you close the switch, you took something that was already at a potential of 12 volts, and you kept it at 12 volts. All right, this is a little bit of a weird one. So before we had light bulbs that were shining at some brightness, and when we close the switch, they stay at the same brightness. So when we close the switch there, we just happened to connect points of equal potential. So it didn't do anything. It didn't change any of the current drawn through the bulbs, didn't change any of the voltage dropped across them. Shall we go on? Let's go to 5 and 6. Maybe these are easy, maybe not. Let's write down some equations for power, just so we know what power is. So power, one way to write power is I times V. All right, and because we know V equals IR, we can also write P as I squared R. We can also write P as V squared over R. All right, so that's just using Ohm's laws. That's just inserting Ohm's law into I equals V. So I could solve for I, right, and that would be V over R, and that would give me V squared over R. I can solve for V, right, and you just plug the I, R in there, and you get I squared R. So these are two equivalent ways of writing power, and we have IV. So in 5, what we have is we have resistors being added in series, one after the other, and the question basically is what happens as you keep adding them. what happens to the power dissipated? We have our power equations over here. 6 is same question, but what happens as we keep adding resistors in parallel? Remember, these are perfect power supplies. In case 5, as we add more and more resistors, the effective resistance of the circuit, we add them in series, so it's this R plus this R, that's 2R, 3R, 4R, 5R. It keeps going up and up and up. What that's going to do is that's going to draw less and less current from the voltage source. You can imagine you keep adding so many resistors that it's as if the circuit isn't closed. I guess that's not shown here. What we need to ask, or even maybe we even draw that in here, is that we eventually close it. So let me draw that here. These things do get closed. We're just adding so many in between, and then asking what happens as we keep adding it. So back to this one, back to 5. As I keep adding this and then close it, the more I have, the less current. The more resistors I have, the less current this circuit draws, the less power gets dissipated. And so what I was saying before, you can imagine you add so many that it's as if there's so much resistance here, it's an open circuit. So no current gets drawn and no power gets dissipated. This is opposite to this the parallel circuit here. As you remember your rules of adding resistors in parallel, the more you add in parallel, the more the resistance goes down. All right. So if we add 2 resistors in parallel, the resistance is a half. We add a third, we're going to get a third. It's going to keep on decreasing and decreasing and decreasing. And as the effective resistance of this circuit decreases, we're going to draw more and more current from the battery. We're going to have the same voltage drop across each resistor, or the effective very tiny resistor, and that's going to draw a lot of power by either of these equations. All right, so you can imagine R is getting very tiny, or I is getting very big. So the circuit 6, as you add more resistors, you dissipate more power. If these are light bulbs and the circuit can handle it, they're gonna actually glow brighter and brighter and brighter. In this case, the light bulbs are gonna glow dimmer and dimmer and dimmer. So if you wired your house like this and you kept adding appliances, each one you keep on, everything is going to get dimmer and dimmer and dimmer. Sometimes that seems to happen in your house that's wired in parallel, just because you're pushing the voltage source. But if you weren't, you'd be able to indefinitely draw current and keep everything running at the same voltage drop, and just keep splitting current down this to keep the devices running. Okay, let's move on to the next one. All right, this is the last one of the light bulb problems. And what the question is here is, what is the brightness of B and C combined? So what is the combined brightness of these two compared to A? Pause it for a little bit. Maybe you might even want to do a little bit of quick math, or maybe you can see this one already. All right, the answer to this one is B and C combined are half the brightness of A. We're assuming brightness is equivalent to power. Let's use some quick Ohm's law to check this one out. Okay, so if I look at the power dissipated by A, I'm just going to use P equals IV here. I'm going to say that A is going to draw, because it's less resistance, it's just one resistor here, it's going to draw 2/3 I. So what I'm going to say is that there's I going into that junction where it's going to split. Okay, so 2/3 I here, the current down here, and so then it's going to split at the junction. All right, and so then we're going to have some current go this way and some current this way. So the current going here is going to be twice as much as the current going here, because the resistance is half as much. All right, and so then the current down here is going to be 1/3 I. Okay, the voltage drop across resistor A is going to be 1 whole V. All right, so we should have put that in here. This says voltage V, and so the two resistors in combination, these two get a whole V, but this one gets a whole V. All right, so let's multiply this one. This one's going to get a whole V. Oops. Let's erase that and use the same color. Okay. Oh, maybe it'll go. Okay, so there's the power for A. That's going to equal PA. All right, so B and C though, it's going to get half the voltage. Okay, so it's going to get V over 2, that's one of them, plus another 1/3 I V over 2, because each B and C get half the voltage that A gets. And so together that's going to equal, so that's 1/6 plus 1/6, that's going to be 1/3 IV, and that's going to be B and C combined. Okay, so B and C get 1/3 IV power. That's their combined power, as opposed to 2/3 as A. Okay, so A is going to be brighter. It's going to be twice as brighter. You could also do this using V squared over R or I squared R, and you'll come to the same result as well. That's it for the light bulb problems. In fact, we're going to save the Thevenin and the voltage divider for the next lesson, since this is getting a little long. See you next screencast.